Okay, AP Physics Review. The first unit of the year, 1D Kinematics. Kinematics essentially means motion. And one-dimensional means pretty much an object is moving left and right only, or maybe the object is moving up and down only. We'll save two-dimensional kinematics for the next review. The first thing you need to be able to distinguish between is distance and displacement. Distance is the total length traveled, and displacement is simply from where you start to where you end. The big difference here is that distance is a scalar, just a size, and displacement is a vector, so it's a size and a direction. Try the first problem on your own, pause the video, and once you finish the first problem, start the video up to check your answer. So go ahead and pause the video now. Okay, you should have worked out this problem. A hiker hikes 25 miles due north and then all the way back to the starting point. So here's the hiker. The hiker hikes 25 miles north, turns around, and hikes another 25 miles back to where he started from. So how far does the hiker hike? Well, this is asking for the distance. Simply the total length traveled, 50 miles. What is the hiker's displacement? Displacement points from where you start to where you end. It's a vector. Well, if we start and we end at the same point, the displacement is 0. Now, to find an object's average speed, we take the distance and divide by the time. And to find an object's average velocity, we take the displacement and divide by the time. Average speed, again, is a scalar. Average velocity is a vector. Try the next problem. Pause the video, play again after you've tried the problem. Go ahead and pause now. Okay, you should have attempted this problem. A truck traveled 400 meters north in 80 seconds. So the truck drives 400 meters and it takes 80 seconds. And then the truck travels 300 meters east. 300 meters to the east in 70 seconds. We want to know what is the magnitude of the average velocity. Okay. So average velocity is the displacement over the time. Displacement is from where you start to where you end. So here's where we're starting from, and here's where we're ending. So the displacement is a vector like this. And so we could figure out the displacement using Pythagorean theorem, square the legs, add them up and take the square root. Or we can recognize that this is a special triangle. It's a 3, 4, 5 triangle, so the displacement is 500 meters. Pointing in this direction. So 500 meters divided by the total time, which is 150 seconds, is going to give us something pretty close to 3.3 meter per second. Choice B. Okay. Acceleration is any time your velocity changes. Now remember, velocity tells you both the speed and the direction. So you're accelerating if you're speeding up, slowing down, or even if you're only turning because your direction is changing. All of those would count as acceleration. Definition of acceleration is change in velocity divided by the time. Give this problem a try, pause the video. Okay, you should have tried this problem. In which of the following situations would an object be accelerated? 1. If it moves in a straight line at a constant speed. Well, the direction is constant and the speed is constant, so that is not accelerating. I'd say that's false. It moves in uniform circular motion. If we're going in a circle, we're turning, so that would be true. Our direction's changing. If it travels in a projectile in a gravitational field, well, I know that if it travels in a projectile, a path like this, the direction is definitely changing. So that's also going to be true. So 2 and 3, both of those have changing directions. And the third one also has a changing speed. To solve problems involving a constant acceleration, we use the 3 kinematic equations, which I call the 3-star equations. These should be memorized. Try this problem using kinematics and the 3-star equations. Go ahead and pause the video now. Okay, you should have attempted this problem. A body moving in the positive x direction passes the origin at time equals 0. So here's the origin, and at time equals 0 we pass this point. Between t equals 0 and t equals 1 second, the body has a constant speed of 24 meters per second. Well, if we're going at a speed of 24 meters per second for a time of 1 second, that means we cover 24 meters in that time. And at 1 second, the body is given acceleration of 6 meters per second squared in the other direction. And we want to know what is the position at 11 seconds. So I'm going to use my 3-star equations, and I always make a chart. Displacement, final velocity, initial velocity, acceleration, and time. The initial velocity is given. The object is traveling 24 meters per second to the right. In this problem, I'm calling right positive and left negative. The acceleration is 6 meters per second squared in the negative x direction. So that's the left, negative 6 meters per second squared. What I would like to know, I'm looking for the final position, so I need to try and find the displacement. That's my goal. But I have to know one other thing. I can never solve these problems only knowing 2 things. So I need one more thing. I don't know the final velocity, so I need to figure out the time. At 1 second, I'm here, and I'm looking at the end at 11 seconds, so the time of acceleration is going to be 10 seconds. So which star equation can give us the displacement if we know these 3 variables? I'm going to take a look at my second equation. Displacement equals v naught t plus 1/2 at squared. Displacement equals 24 times 10 plus 1/2 times negative 6 times 10 squared. That gives me 240. This is going to give me a negative 300. And so I get a displacement here of negative 60 meters. Okay. Now that's not an answer choice. If you notice up here, there is no negative 60 meters because we started at 24 meters. So 24 meters minus 60 meters is going to give me negative 36 meters. And that's my final answer. Another big part of kinematics is being able to graph motion. You need to be very comfortable with position, velocity, and acceleration graphs. If we have a stationary particle, that means it's not moving. The velocity, I'm going to start with the velocity graph, is 0. It's not moving. And the position graph, it has whatever position it's at, I'll call it x naught, that position doesn't change because it's stationary. And of course the acceleration is also 0. A particle moving with a constant velocity, again I'm going to start with the velocity graph. It has some velocity, v naught, and it's constant. It keeps that velocity the whole time. I get the acceleration graph by looking at the slope of the velocity graph. So the slope here is 0, the acceleration is 0. For the position graph, I know that the slope of the position graph gives me the velocity, so I need to have a constant slope. Now a particle moving with a constant acceleration. Okay. I'm actually going to start with the acceleration graph. It has some acceleration, a naught, and it's constant. The slope of the velocity graph gives me the acceleration, so I know that the velocity has a constant slope. In the position graph, the slope is increasing. The slope here gives me the velocity, and the velocity is increasing. Here's the three or four rules that you should be very familiar with. The slope of a position time graph tells you the velocity. A slope of a velocity time graph gives you the acceleration, and the area underneath a velocity time graph gives you the displacement. These three are very, very, very important. Okay. Every once in a while, you might need to know that the area under an acceleration graph gives you the change in velocity. Okay, try the next problems involving kinematics graphs, the next 1, 2 problems. Go ahead and pause the video now. Okay, you should have attempted these 2 problems. The displacement of an object is shown as a function of time. Okay, the acceleration must be, so this is a position time graph, and the slope of a position time graph gives us the velocity. Here we have one slope, which means we have one velocity. Well, since acceleration means change in velocity, and I only have one velocity, the acceleration must be 0. Moving on to the second problem. Here we have a velocity time graph, and it's asking at what time after time equals 0 does an object pass through its initial position. Okay. So since it's asking about position, and I see that it's a velocity time graph, I know that I'm going to be looking at area, because the area under a velocity time graph equals the displacement. Okay. So during the first second, I have a negative area. Okay, I can find that using the area of a triangle. So 1/2 base times the height. Okay, and that would be 1/2 times 1 second times the height is -1. That's the height of the triangle. And so during the first second, we move 1 meter to the left because it's a negative area, 1 meter to the left. During the next second, I look at this area here. Again, triangle, 1/2 base times height. 1/2 times 1 second, that's the base, and the height is 2. So this gives me an area of, I'm sorry, up here, this was -1/2 meter. I apologize. And down here, this gives me a +1 meter, meaning we're moving 1 meter to the right. So if you think about, we start at the origin, and this is -1/2, -1, -3/2. During the first second, we move 1 meter to the left, 1/2 meter to the left. Then during the next second, we move 1 whole meter to the right. The problem asks, when do we pass through our initial position? This is the first second, this is the second second. So sometime between 1 and 2 seconds, we're passing back through the origin. Okay, free fall. There's no difference when you solve a free fall problem than solving any other acceleration problem. The only rule here is you know that the acceleration is automatically 9.8 meter per second squared downward. So the problem may not tell you the acceleration, you just need to know that. It's important when you do a free fall problem to define your directions. Conventionally, call up positive, down negative, but if it makes a problem easier, you're welcome to define down as positive and up as negative. Just be consistent throughout the whole problem. Try this example. Go ahead and pause the video now. Okay, you should have attempted this problem, this free fall problem. An object is released from rest on a planet that has no atmosphere. That's just telling me no air resistance. The object falls freely for 3 meters in the first second. Okay, so set up your chart. Displacement, initial velocity, final velocity, acceleration, and time. Anytime we release something, the initial velocity is 0. I know the time is 1 second. I know the displacement is 3 meters. I'm going to be calling down positive. So it travels down, so the displacement is a positive 3 meters. We would like to know what is the acceleration. We're looking for this right here. Think about what equation you want to use, which of your star equations you want to use. I'm going to use the second star equation. Displacement equals v naught t plus 1/2 at squared. V naught is 0. Cross out that term right away. The displacement is 1/2 at squared, and we're solving for a. A equals 2 times the displacement divided by the time squared. The displacement is 3. The time is 1 squared. That gives us an acceleration of 6 meter per second squared downward, since it's positive, or choice C. Free fall is very symmetric. The time it takes to travel upward is going to be equal to the time it takes to travel downward. If I throw an object up at 10 meter per second and then I catch it, when I catch it, it lands in my hand at 10 meter per second. So the motion in free fall is nice and symmetric. The same time up, the same time down, the same speed when it leaves my hand is the same speed when it comes back to the ground again.